So, by way of background, when I decided to go to Mississippi State and do my PhD, I went there because I wanted to do software engineering. It was one of only 3 schools in the country that you could do your doctoral work back then in software engineering, RIT and University of Washington being the other ones. And when I was there, they required that you have a second area of expertise, and through serendipitous means, I chose AI. And so I've been teaching undergraduate AI for about 20 years, and so what I decided to do this morning is geek out a little bit and take some of my slides from day one, even though I haven't taught AI for about 4 years, and just go over some history of AI, because I think it's very helpful to understand the history of this subdiscipline of computer science so that you can really see where we've been. And where we've been is on a big roller coaster ride. If you look at the history of AI, it's had its ups and downs. In fact, there have been periods in history that have been characterized as AI winters, where you couldn't get funding for anything. So I've got a bunch of books in my office, and I just grabbed some of them off the shelf and said, what do the authors of undergraduate AI textbooks typically give as a definition of AI? And these are 3 of them. I'm going to get to a couple more. I don't know what you think about these definitions. I personally have always liked Elaine Rich's, the study of how to make computers do things which at the moment people do better. And the reason I like that one is because of its time relativity. Because when I was an undergraduate student, word processors first came out. The first PC was introduced while I was an undergraduate student. So I started programming on punch cards, and by the end of my undergraduate career, we were using personal computers, and I couldn't believe that we could actually compile a COBOL program on a personal computer. That seemed unbelievable to me. Well, the idea of a grammar checker or a spell checker at that time was considered AI, especially the grammar checkers. That was, nobody considers that AI today, right? That's just a standard tool. So I think Elaine Rich's definition kind of gets at that. So now, what about John McCarthy? So a lot of people consider McCarthy kind of the father of AI. I've seen some interviews with him, and he is attributed by the Dartmouth group as being the person who coined the phrase artificial intelligence, but he doesn't remember it, according to the interview. But this is his definition of AI. And clearly he's not constraining himself just to that which is biologically observable, but I think a very good definition and a more timely one. So that's McCarthy. I personally marked the beginning of AI with Alan Turing. And most people in popular culture know Turing through the movie The Imitation Game. And but in 1950, Turing wrote a paper in a British journal of the mind, and it was called, let me see if I can get this right. It was called Computing Machinery and Intelligence, was the actual name of the article. But most people refer to it as Can Machines Think, because it is, if you read the paper, his opening salvo is the question, can machines think? And he decided that rather than get into defining AI and defining the semantics, that he would propose this, what we call the Turing test for intelligence now, but he wasn't so arrogant as to name it after himself. He just called it the Imitation Game. And I'm going to assume that everybody in here is familiar with the Imitation Game and how that's played. But I thought that was fascinating that Turing himself decided to sidestep the question of even defining what we're trying to do, which with respect to having machines be intelligent. He said, I just don't want to get caught up in these semantic arguments. I'm just going to propose a game. And if you can build a computer that can successfully play this game at a human level, then that's an intelligent machine. And so hence we have the Turing test. By the way, I highly recommend this paper. I require my undergraduate students to read it during the first week of an AI class, and here's why. And if you don't have a copy of the paper, just email me and I'll send you a PDF copy of it. It's a really interesting read for several reasons. One, if you have a background in AI and you know things like you understand genetic algorithms, for example, or you understand neural nets, or you understand machine translation, he actually lays out all of the major sub-areas that we endeavored in artificial intelligence in the decades after he wrote the paper. So it was very prophetic in terms of what he did there. So I actually mark the beginning of AI as 1950. But if you read most textbooks, they'll mark it at 1956, when this group of three started the kind of the summer workshops at Dartmouth College, just 50 miles down the road from where we're standing right now. And again, McCarthy himself isn't even sure that he came up with the term artificial intelligence, but I know Claude Shannon didn't, because he hated the term. He wanted something more like, automated computing or something like that, because he didn't want to go over the top, because he was fearful that we create a discipline where the hype was greater than the reality, and that, of course, has happened in many instances. Well, the next thing up is, of course, we had a crisis in the United States in 1957 called Sputnik, and that, of course, set off a lot of funding from groups like the NSF, and of course, one of the things that AI endeavored to do right out of the gate was to do a lot of Russian translation, and for obvious reasons, since the Russians had built Sputnik. But there were really, computer scientists made some really simple and stupid mistakes. For example, one of the things they did with this project was to assume that words have pat meanings, right? I mean, words don't have pat meanings, right? We know that. We can illustrate this in a lot of comical ways, right? That's a hot car. I can think of about 3 or 4 meanings for that sentence in different contexts, right? It's blowing a radiator hose, it's a hot day, it's a cool car, it's a stolen car, etc. So words don't have pat meaning, they have meaning in context, and humans are very, very good through their common sense reasoning of ascertaining those understandings, but computers, quite frankly, are terrible at it. And so this is my favorite example from history. Someone decided to be a little ornery and feed the first Russian translator just something, in common literature right out of the Bible, the spirit is willing, the flesh is weak, and it came out, of course, the vodka is good, but the meat is rotten. And very humorous, and has the added benefit of being true. So anyway, you can see how that was an unhelpful translation, as it were. So it turns out there was a lot of promise, there was a lot of hype about what we were going to do with AI, but by the 1970s, nobody was very impressed, and in fact, you really just couldn't get much done. Now, what saved artificial intelligence in those early days was the advent of expert systems, rule-based expert systems, things like this MySyn, which was an infectious blood disease program. There was a geologic survey program that actually found some significant underground deposits that really kind of paid for themselves. And then we had another kind of AI winner, and then of course, I think our current rise really began with Watson on Jeopardy. But even that, if you look at some of the early scripts, and I don't know if you're aware of this, but the producers of Jeopardy didn't want to go live right out of the gate with Watson. Are you aware of that? And they said, no, let's do some trial runs. And something very humorous happened during one of the trial runs, and that is one of the human contestants, I think it was Jennings said, gave an incorrect answer. And the game show host said, oh, that's incorrect. And then Watson came in with that same answer, clearly lacking the common sense knowledge that if it's wrong for Jennings, it's going to be wrong for me. So there obviously was some cleanup that needed to happen with respect to that. So, all right. So what I want to do, this is the last thing I'll do, and then I'll take some questions. Is a lot of machine learning today is somewhere under the covers. There's a neural network. Okay, and we have all kinds of newer versions of neural networks, convolutional neural networks, etc. But here's an example from a textbook in my office of a 3-layer backpropagation neural network. And so it's got some inputs, right, x1 through x sub n, it's got some outputs. And, but the question is, what's going on with these individual nodes within a neural network? This is a fairly simple one. So what you have is this perceptron that learns, and a perceptron, we can think of it as a node in a neural network, and if I were teaching an undergraduate course right now, we would spend about 90 minutes of class time going through this chart. But essentially, I'm not going to bore you with the details, but the bottom line is you've got some inputs, right? And you can see that if I've got these inputs that are binary bit vectors, x1 and x2, and I have a desired output. In this case, I want to produce the results of a logical AND gate. And then I've got some weights. And these weights are generated by a pseudo-random number generator initially. And then we've got a step function here that we've got to go through, and we've got a weight function. We've got a learning rate, which is alpha of 0.1, that turns out to be pretty good. And then we've got a threshold. And basically, we have to go through an iterative process to get through these various epochs, 1, 2, 3, 4, and 5. Think of those as iterations. They're just iterations. We can write a computer program to do this, and it basically trains a particular perceptron to give the desired output for given weights using a bunch of fancy arithmetic, okay? That's the 60-second version of something that would normally take 60 to 90 minutes to go through. So what's the upshot of this? Well, the upshot is that we now, of course, build application-specific integrated circuits, ASICs, that will implement neural nets. And we have a lot of open source software available to implement neural nets, and you actually don't need to know how to program, really. I mean, maybe you learn a little bit of Python. I'll leave to take umbrage with that idea. But I see a lot of people doing this that don't know anything about programming, and that's fine. You don't really need to know how to program in Python to use a neural net. But here's the issue. If you've studied something like linear programming or linear algebra, like I'm sure some of our mathematicians in the room have, you know that those optimization approaches will give you a guaranteed optimum. But using a neural network that uses pseudo-random numbers for weights and tries to train a perceptron within that network, it could fixate on a local optimum and miss a global optimum, right? I think of, we use the example in AI of a blind person who's hiking, right? And you're going up, you're going up, you're going up, and then all of a sudden, you're going down. Okay, I must have been at the top of the mountain, right? But if you've hiked in Vermont, you know that there's a lot of ups and downs to getting to the top of Mount Mansfield, or Camel's Hump for that matter. So that's the notion. And the reason that I bring that up is that Phil mentioned in his opening, and Karen alluded to it as well, the idea that we want to be ethical and that we want to be forthcoming with what we're doing with our systems. So I think what I end with is we need to understand that if we're using one of these tools, whether it's an application-specific integrated circuit designed to implement a neural net, or we're using some open source software tool, that underneath that, there's some technique that is not a mathematically rigorous, guaranteed solution. And so it's possible, and again, we can statistically look at it, we can test it, and we can have a certain level of assurance of how good the outputs are, but we can't really land the plane and say, I guarantee this and I'll rest my life on it. Because there are cases, as we all know, if we look at the history of engineering, and we could just give examples for hours, where some assumption was made, and that assumption turned out to not be true, and we end up with a crisis, right? A building collapses. I mean, one of my favorites that I like to show in classes is the old black and white images of the Tacoma Narrows Bridge collapse, right? And that's there were assumptions made there that didn't account for crosswinds. It worked great on the East Coast, but then we put that bridge design on the Tacoma Narrows, and it never made it past its first week of service. So anyway, those are some of my thoughts on AI, a little bit of the history of AI. I encourage you, if you haven't read Alan Turing's original 1950 paper, it's a good read. It's a fascinating read. He's got the old British kind of verbiage, so you have to get past that. And the other thing I'll mention is that he will often refer to a computer, and he's not talking about an electronic computer. What's he talking about? A person. And usually those people were women. I mean, we had a group of us who were down at the Army Research Labs in the Aberdeen Proving Grounds last week, and And we got to see ENIAC, and of course their new supercomputers are named after all the women who were the first programmers of ENIAC. So in Turing's mind, you know, he actually had a little bit of a gender-specific idea of a computer because most of the programmers were women in the early days, so for what that's worth. So I'll stop there. We've got about 10 minutes, and I don't know if we want to do questions, if we want to break early.
Is there any questions?
Yeah, any questions, comments? Anybody want to take umbrage with my treatment of AI history? You're welcome to do.
So, Justin Custer, lecturer in philosophy. I really appreciate the teaching Turing. We're not philosophy line courses and stuff like that. Was wondering, like, how do you actually approach it with your students? Do you actually say, this is what intelligence is? This is how we're doing it? Because, I mean, that's the invitation test, right?
Yeah,
well,
well,
if we have this behaviorism, or if we trick us into thinking it's intelligent, well, then it must be intelligent.
Yeah, so the last time I taught AI 4 years ago, no one had really agreed that the Turing test had even been passed. And I think a lot of people in this room would say we definitely passed the Turing test by now. What do you think, Ali? No idea. I'm not sure. Anybody want to weigh in on whether that's happened? I think a lot of the newer systems, people would say, yeah, we actually, in the last couple of years, we have built systems that can fool humans sufficiently. So I've never really wanted to get into the semantic arguments about how we should even define AI. I just really present the student, kind of like a philosophy professor, right? We just want to debate. We don't really want to land the plane.
Well, it's kind of interesting to think about actually getting to a definition of that, because if you start thinking about the habits, it's something that Brian and I have been working on developing habits for us, is that if these things are truly intelligent, if they are really sentient things that we need to take into consideration, then we might have moral obligations to these things.
Yeah.
And that could be, I mean, that's kind of serious, right? I mean, if we're actually creating something that we have moral obligations to do, sort of responsibility towards, then it kind of can be important. So,
Yeah, it is.
I understand this.
And that's always been a part of software engineering. So I've got a lot of students going into the healthcare industry, and HIPAA means that they're personally liable for certain things that they build, right? I mean, that's kind of scary.
Yep.
So yeah, I think you're right. On a more practical note, I've been like Turing in that I've kind of kicked the can down the road, and I said, let's just build cool stuff.
Yeah.
One of my favorite ones is I usually teach in the fall, and so I've given them past data of National Football League wins and losses and a lot of statistical data, and then had them build an expert system to try to give them the first 10 weeks of data, and then have them build an expert system to try to predict 4 consecutive weeks of who will win what football games in the NFL based on a ton of heuristics. And then we can do that same thing with the genetic algorithm later in the semester. Then we can do that same thing with a neural network later in the semester and just see how they do. I tell them that your goal is to beat the experts. So we can go say, okay, here are all these sports writers, and here's how they did. Can you defeat them? And no, by the way, I don't ever want to find logic in your program that says, if it's the Jets on the road at Gillette, pick the Jets, because there's this one anomalous time when the Jets won, in Gillette, and they'll write a rule in there to counteract that. It's like, that's no fair. You have to have general rules, not a specific rule that you cherry pick and overtrain your network. Anyway, that's what I do.
And just one more thing, a good complimentary article to Turing's is John Searle's Chinese thought room.
Yes.
Yeah, and that would be the counter argument to this actually being something intelligent. Right?
Yeah, because he was very critical of this. You're right.
Exactly.
Searle was.
So,
Yeah. Good catch. Any other thoughts, comments?